Okay, good afternoon, everyone. Winter is here. I'm really exciting about the snow. All right. Last time we talked about two different methods to solve first order ODEs. So, oops. If you look at the beginning, the ODEs we're focused on is first order, but it's more than one. We have like a total number of n equations lumped together. So all the coefficients are in matrix. So we learned how to use either the inverse Laplace transform, or we can use the so-called eigenvalue and eigenvector method to solve this kind of problem. So I think last time I don't have time to explain how to use eigenvalue and eigenvector. So here I'm gonna go over homework number one. So the first thing is, first of all, when you see a mechanical system, you need to find out the ODEs, or equation of motion. So in this case, there are two ways to write it. You can either write it in as like a bunch of equations, plus k1 plus k2, x1 minus k2, x2 equal to 0, and 2x double dot plus k2, x2 minus k2, x1 equal to 0. So if you don't want to work in matrices, so that's what you're gonna get, because you have two coordinates, you're expecting two equations. So for your convenience in this class, we think about write it as matrix format. So your M matrix is going to be a diagonal matrix. Is your M1, M2, and then your K matrix is going to be symmetric. You have K1 plus K2 minus K2 minus K2 and K2. The reason I can easily write these out is through the coupling of your system. As I said, all the diagonal terms describes how, for example, your entity 1, 1, that means all the springs connect to spring number 1. Oh, sorry, to connect to mass number 1. All the off-diagonal terms, they should be negative, and that describes what's the springs between these two coordinates. All right, so you have M and K. And the first thing we need to do here is, in order to use eigenvalue and eigenvector method, the first step is, oops, convert second order ODEs to first order ODEs. All right. So the way we complete step one is by defining state variables. So for mechanical system, when we talk about state variables, so that means we need to define velocity and position. So depending on how many coordinate systems we have, we might have more than two state variables. So here we have two coordinates, so we need to define velocity and position for both coordinates. So let's say for the state variable, let's use a state variable y. And then let's say y is x1, x2, x1 dot, x2 dot. So here you can see that your column vector is a state vector. It contains all the state variables, position and velocity. Again, there's no unique way to define these state variables. You can change the x1, x2, change their orders. But personally, I recommend you to collect displacement first and then collect your velocity. So this is extremely helpful, especially if you want to work with a matrix. All right, so the step number 2 is write your ODEs in state representation. So what is state representation? You need to find out your y dot equals to some a y plus b u. And then you need to find your initial position or initial state. So A matrix is called system matrix, B is input matrix, and U is your actual input. So in this class, we won't separate B and U. Sometimes we just merge them together. And first of all, let's find out your A and B U for this example. So what is y dot? Your time derivative for state vector is just time derivative for each entity. So position becomes velocity, and velocity becomes acceleration. All right. So then we need to find our A matrix that's to be determined. And then we need to describe your y dot using y. That means we need to use x1, x2, x1 dot, x2 dot to describe it. And then all the terms that has nothing to do with y. So these vector or this matrix is all terms without y. So that means if in your equation you find terms that has nothing to do with x1, x2, and x1 dot, x2 dot, you just consider them as constant and put them in the end. All right. So in this case, let's look at it. Let's find out what the A is. Because your Y is a 4x1 matrix, so your A is going to be 4x4. And what is your x1 dot? Your x1 dot is the third entity of your state variable. So you just put 1 in the third column, all the others are 0. The same thing, 0, 0, 0, 1. And then what is x1 double dot? Then you have to go back to your first ODE. Right? So what is your entities? So the first one is K1 plus K2, 27 divided by 9. So that's about 3. And then you have to move everything to the right so it becomes negative. And then the second entity is just K2 over M1. So that's 1/3. And then it has nothing to do with velocity because we have no damping in it. And the same thing, if you focus on the second equation, you can get the second row. So your second row is K2. The first entity is K2 over M2. So that's 3. And then the second entity is minus K2 over M2. It's minus 3, 0, 0. So that's how you get your A matrix. And then here, because B times U, that's a 4x1 column vector. As I said, you need to find all the terms without x1 and x2. In this case, we cannot find any of these terms. So that's why all the constant terms would be 0. So this one is actually easy. We just need to solve what is y dot equals to what AY. All right. So also we need to find out initial condition. Initial condition is just x1 not, x2 not, x1 dot, x2 dot. So you just lay out the initial condition for each entity in the correct order, and then you copy and paste. You can see it's 1, 0, 0, 0. So that's what we need to solve. So here we need to use eigenvalue or eigenvector method. So what we need to do, the idea for this method is we want to decouple your y dot equal to AY. Because if you look at your, so if you look at your A matrix, you can see that we can find off-diagonal terms in your A matrix. If you see off-diagonal terms in your A matrix, that means your system is coupled. So eventually we want to make sure that your A is a matrix that only have diagonal terms. So how can we do that? we need to diagonalize your A matrix using eigenvalue and eigenvectors. So the idea is we assume that y dot, we can decompose your A into P times lambda times P inverse y. All right. So remember that lambda is a matrix. So whose diagonal terms are eigenvalues of A. All right. So P is also a matrix. So P can be right as U1, U2, all the way to UN. And then UI is ith eigenvector of A. And then UI is also a column vector. So that means overall your P is m by n, but then your UI would be m by 1, right? So how can we find these P and lambda? If you want to calculate this by hand, so in order to find all the lambdas, what you need to do is you need to find out lambda I minus A determinant equal to 0. You have to solve this equation. That's going to give you n total lambda values. In order to find out your UI, you just put in the ith lambda into that equation and then solve that linear equations. So that's how you find lambdas. And then that's how you find UI. So that's how, this is hand calculation. If you want to do this in MATLAB, you just need to use the eigenfunction, the EIG. This function is going to give you two outputs. It's going to give you P and lambda directly. Okay, so that's easy. All right, so let's say, I believe 99% of you is going to use the MATLAB. So let's say you find your P and lambda using EIG function or eigenfunction. Then we can decompose your A matrix into 3 parts. And then after that, you just multiply both sides by P minus or P invert. P invert P lambda P invert Y. All right. So up to this point, you can see that P invert times P, that forms identity matrix. So you can directly write everything as lambda P invert Y. Okay, so then you see you have P invert Y on both sides. And we need to do for step 3, define a new vector Z such that your Z equals to P invert times Y. So that's how we convert values from Y domain to Z domain. You can also reverse it. So that means your Y would be P times Z. So that's how you can see that the P matrix is kind of a coordinate transformation. It couples the Y and Z coordinates. Once we replace your P invert Y with Z, then we're going to have our original ODE becomes Z dot equals to lambda Z. And remember that your initial conditions also follows the same coordinate transformation. So that's why your Z naught equals to P invert Y naught. Because your initial condition was initially in Y domain. In order to convert it to Z domain, you just multiply it by P inverse on the left. All right, so then remember our original question, how far we went. So we first start from the second order ODE. We converted to the state space representation in Y domain. And then we got our equation in Z domain. So why we have to go through this lengthy path? So then if you look at a Z domain, we actually have some very nice properties. So let's write it out. You have Z1 dot, Z2 dot, all the way to Zn dot. So that's your Z dot vector. And then you have your lambda 1, lambda 2, lambda n. All the off-diagonal terms will be 0. That's the property of your lambda. And your Z is just Z1, Z2, and Zn. Okay, we know that initial conditions for each row. So if you don't like matrix format, you can actually write it out into a group of linear functions. The first one is Z1 dot equals to lambda 1 Z1. The second one is Z2 dot equals to lambda 2 Z2, all the way to the last one, the n dot equal to lambda n Zn. And then remember, we also know the initial condition for each and every one. So even though we have n equations here, but each equation is actually independent from each other. Let's say, if you look at here, it's a very simple first order single degree of freedom system, right? So we can easily find out that your Zy t is just Z naught 1 E lambda 1 t. So if you don't recall these, you can go back to your math 333. I believe that's the first ODE equations you solved in that class. Then similarly, you can find Z2t equal to initial condition of the second row. And then all the way to Znt equals to Z naught n E lambda n t. So up to this point, we can find your Zt solution. It's just Z1t all the way to Znt. Because we find the solution for each entity, we just collect them back into a column vector. Then we get the solution for the entire Z domain. So but then this is not enough. We don't want solution in Z domain. We want solution eventually in X domain, or even we want solution in Y domain. But then how can we convert solution from Z to Y? So that's why you have to go back to these coordinate transformation. We can multiply everything by P, then we get the solution in Y domain. That's why your Y is P times ZT. Your ZT is here is n by 1. Your P is n by n. So eventually n is your Y is n by 1. So the matrix dimensions, they match. All right. So let's review this problem again. So basically you need to touch like 3 different domains. The first one is X domain, that's how you originally define your coordinate system in ODE. And then you have to convert from X domain to Y domain. The way you do it is using the state representation. And then from Y to Z, you need to use matrix diagonalization. And you find the transformation matrix P. And then this P is gonna tell you what to do to couple Y and Z domains. And then eventually Z is the easiest domain to work with because everything is decoupled. You can simplify a nth order system into n total single degree of freedom system. All right, so that's the logic of this homework. And I think it's better for you to check my MATLAB code because I already made all of these things automatic. All right. Any questions?
Yep. Yeah, just one quick one. So with the Y dot matrix, could you just briefly go over where you got the first 2 rows?
The first two rows?
Yep.
You mean for the A?
No, sorry. Yeah, for A. Sorry, my bad.
So actually here we have two equations, right? So in this here is a 4x4 matrix. Actually, we need four equations, sorry. So here from the system equation of motion, you get two, but then there are others two by nature.
Okay. Yeah, I was just wondering.
Yeah,
You
got these two, and then you can clearly see that x1 dot is x1 dot, x2 dot is x2 dot. Make sense?
Yep, that makes sense.
Yeah, and last class, I said if you don't want to work in individual equations, actually using this matrix format is much easier to find an A. I can show you why. So let's say directly use n plus kx to find A and Y. All right. So from here, we have one equation, which means your x double dot equals to m inverse minus k x. Nothing special. We just move all the terms, all the x terms to the right-hand side and only leaves x double dot on the left-hand side. And then there's another equation, which is directly x velocity equals to velocity, right? And then let's look at our y. Your y is your x dot, that is 2 by 1, that is 2 by 1, and in total, that is 4 by 1. And then what you can do is you can find out your A matrix. That is the underlying part is your A matrix. And then again, this is a Y matrix. Oh, let's write it as Y dot. We have these. So this is your Y, and then your Y is X over X dot. That's your Y. And then inside of this A matrix, instead of cutting it into 4 by 4, 16 elements, you can actually cut it by 2 by 2. That is 4 elements in total. Let's name it as A matrix, B matrix, C matrix, and D matrix, okay? So for each one is 2 by 2. So that's why in total, your A matrix is 4 by 4. So then, because this is 2 by 1, this is 2 by 1. So this equation, you can write it as x dot equals to A x plus B x dot. The second one is x double dot equals to C x plus D x dot, right? Then from the original two equations, from these two original equations, you can find your A, B, C, and D matrix, right? You just compare the terms. Like here, x dot equal to x dot. So that means here you should get a 0. So that's why your A should be a 2 by 2 0 matrix. And then your B should be a 2 by 2 identity matrix. And then if you compare here, your C should be minus M inverse K. And then your D is again 2 by 2 0 matrix. So this will be extremely helpful if you have more than 2 equations. For example, in this system, if I add another 10 mass to the right-hand side of M2, then you're going, if you want to do these individually, you're going to have like, I would say you're going to have like 12 equations, and then your A matrix will be 24 by 24. And then you have to do these all individually. But then if you use a matrix, you just need to do it twice. because you always cut your A matrix into 4 segments, and then you find the expression for each segment just by doing matrix multiplication. Yeah, so matrix might be hard to understand, but it brings convenience. So you can still solve it without using matrix, by just my recommendation. Any thoughts?
Is this example going to be posted on your YouTube channel?
Yeah, I can do that. Let me stop recording.